Hello and welcome. So with today's quick video, we'll talk a little bit about the topic of moment of inertia. You might have heard these words used before, moment of inertia. Hopefully I can explain it in such a way that it makes sense and what its purpose is. Uh, let's start with this, okay? Something super simple. I'm gonna draw three shapes, okay? Let's say these are the dimensions, the relative dimensions of floor joist made out of wood. I don't know, let's say that this one here is a 2x4. Let's say that this one here is a 2x6. Let's say that this one here is a 2x8. And then I'm going to pick a 2x8. I'm going to draw it like this. Okay, so this here also is a 2x8. Now, here's a question, okay, to get us started. Out of all these shapes, let's say money was no object, which one would be your preferred choice as to, say, would be the structure to support the floor of your home? Say if you lived in a house, which one of these would you select? Well, the options, I guess, the fair ones would be multiple, but it's likely that you would select maybe this one for your floor. You might even consider this one, but definitely not this one, right? Is it fair to say that you would not select this one, right? And tentatively, you see how these shapes here are more appropriate for supporting a floor than say this shape here, right? If you want a floor joist supporting your floor, you want them to be kind of like this in the long direction rather than on the flat direction. And that's because intuitively you have an understanding of how the property called moment of inertia, or second moment of area, but we'll call it moment of inertia, affects a shape's ability to resist bending. So let me see if I can clarify this a little bit, okay? Let me clear things up a little bit and let me draw a shape, okay? So moment of inertia, you and I will define it as a geometrical property. Okay, so it's purely related to the dimensions of a shape, the cross-sectional dimensions of a shape. And it's a geometrical property of a shape that influences how well that shape resists bending. There's a whole bunch of fancy words for saying that somehow I'm going to show you a way that you can actually calculate a quantity that's only related to that shape. And that number that we're going to calculate will give us an idea of whether or not that shape is better or worse at supporting resisting bending. So let's try this, okay? I'm going to draw two shapes. I'm going to call both of them 2x8s. Okay, I'm going to call this a 2x8, and that's going to be 38 millimeters by 184 millimeters. Okay, so that's what this is. And I'm going to call this as well a 2x8. Okay, so I'm just going to put that right here. 2x8, 38 millimeters by 184 millimeters. Okay. So this is the nominal size of lumber in Canada. Okay. All right. I'm going to give you this formula now for moment of inertia. Moment of inertia, the symbol for moment of inertia is I, capital I. Okay. And the formula for it is for this shape, a rectangle, BH cubed divided by 12. So to make sure that I am passing on to you exactly what I mean, for a rectangle, I is equal to, the numerator is B times this H cubed all of that divided by 12. Okay, where this here is h, the height. Okay, this here is b, the base. Okay, this here is h, height. And this here is b, the base. So you and I together now are going to calculate the moment of inertia for this shape right here. Whoops, pardon me. For this shape right here, and then we'll calculate the moment of inertia for this shape right here. So let's do it for the deep beam. Okay, so let's do it for this shape first. The moment of inertia is equal to BH cubed divided by 12. So B is 38 millimeters times H. The height is 184 millimeters. I'm just going to extend this a little bit. That. And that height also has to be cubed. Then all of that has to be divided by 12. Now we're going to do it together in real time. I'm going to do it while you try it out as well. And let's see, 38 times 184 cubed. All of that divided by 12. Okay. All right. Now I get a big number. I think you would too. I'm going to write out the huge number right now. Okay. Okay, it keeps going. 6666666. And the units are millimeters to the power of 4. Okay. Now you can see this is a huge number in millimeters, right? It's 19,726,762. So 726,762.6 periodical. So typically when it comes to moment of inertia in metric units, you actually express it using scientific notation. So it's a number times 10 to the power 6. So in our case, it would be this. And this is millimeters to the 4th. Okay, so it'd be simplified as 19.727 times 10 to the 6 millimeters cubed. Okay, so now here we calculated the moment of inertia of this shape. Okay, we had the base, we had the height, and then we simply used the formula and plugged those numbers in. We did a best 2 out of 3 to make sure we didn't mess it up, right? And then we give it out. Not bad, right? So let's try now maybe doing this. Okay, let's repeat this process, but let's calculate the moment of inertia for this one. Great. So let's go here. Moment of inertia for this shape is the same formula, right? So BH cubed divided by 12. Now, look at this though, because we've shifted the beam and rotated it at 2 by 8. Now, the base is that long direction. So it is 184 millimeters. The height is now that short direction, which is 38 millimeters. So that's going to be cubed. And then all of that gets divided by 12, just like this. Okay? Because it's on its side. So we're going to do this together live in real time. 184 times 38 cubed. All of this divided by 12. All right, big number, but it's smaller than the previous one, huh? I get this number, 841,370.6666666 period, right? Millimeters to the power of 4. Okay, so if we express this in the same format using scientific notation, a number times 10 to the 6, it would look like this. 0.841 times 10 to the 6 millimeters to the power of 4. Now look at this. Okay. Compare this number against this number. Do you see how this number is much, much higher? It's the same shape. Both of these are 2x8s. The only thing that was different is that for one of them, we have them on knife edge, and for the other one, we have it on the flat long edge. Which ones of the two would you have supporting your floor? Well, I suggest that it's likely this one and not this one, even though it's exactly the same shape. And that's because you have an inherent intuitive understanding of what a moment of inertia is. A moment of inertia is a geometric property. So look at this. This value, way, way smaller than, say, this value. And it's the same shape. And it's purely related to the geometry. Okay? So that's all there is to the moment of inertia, and that's all we're really going to cover about it. It's a geometric property that gives us a quantity, a quantification of a shape's ability to resist bending. Okay, purely geometrical. Right? That's it. That's all I wanted to cover about this. I want to thank you so much for your time. Take care and have a lovely day.